Welcome to this talk on DP Sniper, a tool to automatically discover violations of differential privacy. My name is Benjamin and this is joint work with Samuel, Ilya and Martin. We are all from ETH Zurich. First, let me give you an intuition on differential privacy. In this scenario, a hospital is storing sensitive medical records in a database and plans to release statistics on this database, such as the number of patients with a certain disease. In this scenario, the patients in this database might be rightfully concerned about the use of their private data to produce publicly available information. Differential privacy suggests a solution to this concern, which is obfuscating the output by adding an appropriate amount of noise. In this case, the output is no longer a deterministic value but follows a distribution, and it is now much harder to infer sensitive information from samples of this distribution. One of the most common mechanisms to enforce differential privacy is the so-called Laplace mechanism, which samples Laplacian noise and adds this to the true output. While the Laplace mechanism is differentially private in theory, in practice most implementations suffer from floating point vulnerabilities. Intuitively, this is because the least significant bits of this floating point value reveal more information than you would expect if you analyze this from a theoretical point of view. Even though this attack has been known for at least 8 years, existing analysis tools cannot discover it. This means that if you analyze this code snippet using existing verification tools for differential privacy, they would incorrectly claim that this code is differentially private. Similarly, if you apply testing tools for differential privacy, they would not find any violations, leading you again to mistakenly believe that this code snippet is differentially private. This, among other reasons, has been the inspiration for this work, DP Sniper, which now correctly identifies that this code snippet is not differentially private due to the discussed floating point vulnerability. At this point, I should point out that DP Sniper is not restricted to floating point vulnerabilities or floating point attacks. It also covers other vulnerabilities as discussed in previous testing and verification tools. Now, before we dive into details of DP Sniper, let me first provide you with a more accurate description of differential privacy. As discussed, the differentially private mechanism produces a sample from a public value given a private input. However, it protects the privacy of individual users in the database as follows. If a certain user, Alice, debates whether or not it's okay for her to enter her data into the database, she should compare the two scenarios, one scenario where the mechanism is being applied without her data, and another scenario where the mechanism is being applied on a database that includes her data. Of course, the two output distributions will be slightly different, but differential privacy guarantees that the distributions are roughly the same, meaning that intuitively it doesn't really make a difference whether or not Alice enters her data into the database or not. More formally, differential privacy ensures that the probability of obtaining an output in any given set S is roughly the same regardless of whether the database includes the data of Alice or not. In this scenario, the terminology is that M is a mechanism, for example, counting the number of patients with a disease and adding Laplacian noise, and S is being called an attack because it formalizes an attempt to infer whether Alice was in the database or not, and this then this equality or approximate equality in this case indicates that the attacker cannot really distinguish these two scenarios. Now, even more formally, we would say that M is epsilon differentially private, often referred to as epsilon dp, if for all pairs of inputs A and A prime, which are neighbors, where this neighborhood here captures the fact that A prime is obtained by adding or removing the data of an individual user from A. And for every attack S, the logarithm of the probability that M of A lies in S minus the logarithm of the probability that M of A prime lies in S is at most epsilon. And as discussed, this intuitively indicates that these two probabilities are roughly the same. However, in this talk, we focus on our newly coined term of differential distinguishability, where we would say that M is psi differentially distinguishable, referred to as psi dd, if there exists A and A prime and an attack S, such that this expression here is at least psi. So differential distinguishability is almost the opposite of differential privacy, except that we have a greater or equal here instead of a greater than. So this results in a search problem for differential distinguishability. Namely, we want to maximize this term by as much as possible. And in order to do this, we can maximize over possible neighboring inputs A and A prime and possible attacks S. And the higher this value is, the higher is the differential distinguishability of our mechanism M. Luckily, there already exists a ton of work on maximizing potential inputs. There are exhaustive approaches, sampling approaches, and some heuristics. And in particular in this work, we rely on the previous heuristics that were already established for the input search by StatDP, which we cite here. However, maximizing the attack is much more challenging and is in particular also needed for floating point attacks, because finding a strong attack or a powerful attack requires accounting for these floating point vulnerabilities, so picking this S in order to account for floating point vulnerabilities, which no one does at this point. So in this work, we rely on existing work for this part, leaving us only with the problem of maximizing the power of a certain attack, as shown here. So the goal of our work is finding an optimal attack. Now, how can we achieve this? First of all, we can observe that in order to maximize this expression here, we would like to minimize this expression here because it's being subtracted, which means that we would like to minimize this probability here. Unfortunately, we have to be careful here, because if we are too successful in minimizing this probability and it gets really tiny, then we will no longer be able to accurately quantify this probability, because we can only estimate this, and estimating small probabilities is hard. Therefore, we only target a small constant c here, so we try to make this probability as small as possible, but not smaller than c. On the other hand, we of course try to maximize this term, which means that we will have a trade-off between minimizing this term and maximizing this term. What does this mean for a potential attack? Intuitively, we would like to compose the attack S of elements which are likely to result when the input is A and unlikely to result when the input is A prime. This means that an element, candidate element B of S, should be in the set if and only if the probability that the input was A is high, given that the output is B. This has some deep connections to the Neyman-Pearson lemma, which is discussed in more detail also in the publication. So this has been the first key insight, namely that given this posterior probability, we can actually know which elements that our attack set S is optimally consisting of. And the second key insight of our work is that we can actually estimate this probability by training a classifier. So note here that we can actually easily generate training data automatically as much as we want by just running this mechanism M on inputs A and A prime. And this means that it is fairly easy to use the standard framework of machine learning to quantify this probability. Now, overall, this results in the following workflow for DP-Sniper. First, DP-Sniper trains a classifier for this posterior probability. For this, in our evaluation, we use neural networks and logistic regression, so really standard stuff from machine learning. In a second step, we transform this classifier into an attack by picking the elements of of the attack set S by picking them exactly if the posterior probability is above some threshold t. So all that remains to do in a third step is selecting t, and in order to do this, we ensure that this probability is exactly c as discussed before. This probability should be really small, but not below some value of c. In our publication, we derived the following guarantee, which is informally stated here. DP Sniper finds an approximately optimal attack. So here, approximately is quantified mathematically here, so it's well defined what this means. However, we have two key assumptions that allow us to make this claim. First of all, we assume that we cannot estimate tiny probabilities. As discussed before, this would not be realistic, so this is a reasonable assumption. And second of all, we assume that the learned classifier is perfect. In other words, we assume that machine learning works. Of course, this is a strong assumption in practice, which is why we also made sure that our guarantee degrades gracefully, so we even get strong or interesting guarantees in the case where the learned classifier is imperfect. Now, in order to discuss related work, let's first consider again our small example of this floating point vulnerability here. What we can learn from this attack is that black box approaches are more convenient, especially if we are dealing with floating point arithmetic. This is because if we don't have a black box approach and we have an approach that actually investigates the code here, we need some sort of model, in particular also of this Laplace distribution, which will be very hard and probably incorrect because such a model is likely to assume idealized arithmetic. Instead, if we just have a black box approach, analyzing this code is much simpler. We simply need to run it. Now, if we look into related work, unfortunately for most existing testing tools for differential privacy, a black box approach is insufficient. Only for StatDP, DP stochastic tester, and this work, our black box approaches are sufficient. However, DP stochastic tester only supports one-dimensional outputs, so it's not a great fit in general. Now, StatDP is grayed out here because it's only semi-black box, but in practice that's not a big concern. We can consider it as being black box, and this is why in our evaluation we compared DP Sniper to StatDP. Now, looking into the evaluation, we see here on the x-axis, we see the level or amount of differential distinguishability we were able to infer, and on the y-axis we see various algorithms. Now, the takeaway message here is that DP Sniper and StatDP perform similarly, but this is because all of these algorithms were already evaluated in StatDP. If we move on to a more advanced algorithms, such as, for example, a rapport or one-time rapport, these are state-of-the-art differentially private algorithms, then DP Sniper significantly outperforms StatDP. For example, here in one-time rapport, the level of differential distinguishability of DP Sniper is much better than that of StatDP. I should point out here that we were not able to run StatDP directly because it doesn't exactly implement what is needed to derive differential distinguishability, which is why we fixed it in a version StatDP fixed. And still the fixed version is being outperformed by DP Sniper. Also, it's important to note that DP Sniper is 15 times faster, so the increased power of DP Sniper does not come at an increased cost in runtime. To conclude, we have presented a new approach to discover differential distinguishability. Our approach comes with optimality guarantees, and our code is publicly available. In our evaluation, in addition to showing that we outperform StatDP or StatDP fixed, we also demonstrate that we can successfully derive differential distinguishability in this case, and we are the first to do so. Thank you for your attention.